In this video, I'm going to show you how to evaluate an argument using the direct truth table method. So we've moved on from evaluating statements to evaluating whole arguments, which entails, in this case, three statements: premise one, premise two, and the conclusion. And we're going to evaluate this argument to determine whether or not it's valid. So we've already got the argument symbolized. Premise one, if L, then P. We could just say L stands for you loan me $20, pay you back tomorrow. So if you loan me $20, I'll pay you back tomorrow. Premise two, you loan me the $20 and the conclusion is I pay you back tomorrow. So it's already symbolized for us. And you see that it's stacked vertically. The statements are one on top of the other. And this is our standard formulation of the argument. So our first step is going to be taking that vertical form, that stacked form, and laying it out horizontally. So our first move is to take the stacked argument and rewrite it horizontally on the truth table. So we're going to take this form of the argument, we're going to rewrite it horizontally right here. So let's start with premise one. If L, then P. You're going to put premise one on the left side here. If L, then P. And you're going to separate the premises with a slash mark, just one. So the next premise, L, the atomic sentence L, is going to go right next to that. And then you're going to separate the premises, in this case there's two, from the conclusion with a double slash mark. And then you're just going to write the conclusion next to it. So there's the argument laid out horizontally. You've got premise one, P1, if L then P, laid out horizontally, separated with a slash mark. Then you've got premise two, L, next to it. And then the conclusion, P, is separated from the premises. So again, lay out your premises, separate the premises with a single slash mark. And when you've got all your premises done, your conclusion is separated from the premises with a double slash mark. Now, you count up the number of atomic sentences here. You've only got two, even though you've got a compound premise and two atomic sentences. So you've really only got two atomic sentences, and you're going to place those over here on the left-hand side. So whatever ones you got in an argument, you're going to put them on the left side. So we've got L and we've got P. Now that we've got our argument laid out horizontally, we don't need the stacked version anymore. So let's just get rid of that, getting us ready to move to step two. But just to keep things clear, since we're still learning, this is premise one, if L then P. L is premise two, and P is our conclusion. You don't need to do that, but since we're just learning this, it might be helpful. Our next step is to apply all the possible combinations of truth values for our atomic sentences of the argument by row. So our next step is to add all the possible combinations of truth values to the rows of the atomic statements. Since we have two atomic statements and our truth values are binary, meaning they're either true or false, there's only two, the number of rows, 2 stands for the number of truth values, so one for true, one for false. N stands for the number of atomic sentences, so we got 2 here. So the number of rows is going to be 4. Again, the 2 stands for the fact that we're using binary truth definitions, so true and false. N stands for the number of atomic sentences, and that gives you the number of rows that you need for the truth table. So we add all the possible combinations of truth values by row. So for me, the easiest way to start is when they are both true, where L is true, and in this case, P is true. And then the next row, L is true, P is false. The third row, L is false, P is true. Got to have that combination. Let's clean that up a little bit. And then the last combination to capture all the possible combinations is when they're both false. And now we're ready to get to work using what we learned about how to determine the truth values for statements. And we apply each row of truth value to the argument. Okay, so step 3, we're going to apply the rows of the truth values to the statements of the argument. So there's 2 ways you can do this. You can do premise 1 first and just go down row 1, 2, 3, and 4, or you can do it by row where you apply the truth values from row 1, where L is true and P is true, and you apply it to premise 1, then premise 2, and then the conclusion. I like doing each statement by row. I don't know, for me it's just simpler to think about each statement and the rules of how to determine the truth value for each statement. So I can just do all of premise 1 and then move to premise 2 and then move to the conclusion. So that's how I'm going to demonstrate it. So as we can see, our first premise is a conditional. So I got to think about how do I determine the truth value of a conditional statement? And I remember that a conditional statement is true at all times except when the antecedent, the first statement, is true, and the consequent, the second statement to the right of the arrow, is false. And that's row 2. All other times, it's true. So I'm just going to plug in those truth values under the main operator, the arrow, according to that rule. So for row 1, where L is true and P is true, that conditional is true. Row 2, where L is true and P is false, that's the only time this conditional would be false. I put that under the main operator for premise 1. And then we know row 3 and row 4 are both true according to our understanding of the logic of the conditional. So premise 1 is done. Let's move to premise 2, which is simply the atomic statement L. So determining the truth value of L here is just according to the truth value over here of our atomic statement. So we just follow along. So in row 1, L is true, so we put it under L. Row 2, L is true, so we put that under premise 2, which is L. And then row 3 and 4, L is false. So we just apply that under premise 2. And similarly, the conclusion is simply the atomic statement P. We just follow that row by row. So row 1, where P is true, we put true under P, the conclusion. Row 2, it's false. Row 3, it's true. And row 4, it's false. So that is complete. Our truth table is all complete. We've added all the possible combinations of truth value, and we've plugged it into the form of the argument so that every single combination of truth value that's possible has been applied to the form of the argument. So our next step, step 4, is going to be interpreting the truth table to determine validity. Interpreting the truth table to evaluate whether this argument is valid or not. The last step in evaluating arguments using the direct truth table method is step 4. It's our last step. And in this step, you interpret the truth table to determine whether the argument is valid. So let's quickly go over what a valid argument is. An argument is valid when its form does not allow the possibility of having all true premises and a false conclusion. And since we plugged in the truth values, all the possible combinations of truth values for the atomic sentences L and P into the form of this argument, that is, into premise 1, into premise 2, and into the conclusion, now we look to see if it's possible for this argument to have all true premises, in this case, both premises true, and the conclusion false on the same row. So that's how we're going to test out this form. Remember, it's a matter of form, not a matter of content. So no matter what L and P stand for, you could switch these letters out to P and Q, A and B, anything. But if it has this form where you have a conditional in the first premise, the antecedent of that conditional in the next premise, and then the consequent of that conditional in the conclusion, this form would apply to any argument that has this type of form, no matter the content. So we look to see if it's possible for it to have all true premises and a false conclusion. Any row, just one single row of having both premises true and the conclusion false, or all the premises true and the conclusion false, then that argument is invalid. So when we look at this, we look at row 1 here, and then we look, premise 1 is true, premise 2 is true, and the conclusion is true. So far, so good. Next row, row 2, well, the first premise is false. So on this row, it cannot ever have the possibility of all true premises because the premises are not true. So row 2, everything looks fine. Row 3, premise 1 is true, premise 2 is false, and the conclusion true. Well, again, we don't have all true premises. So there's no possibility for at least the first 3 rows here to have all true premises and a false conclusion. And then row 4 also confirms this because we don't have all true premises. We do have a false conclusion, but we don't have all true premises. So this is a classic example of a valid argument. And the form is so common, and the form is valid for all arguments of this form. It's called a modus ponens, abbreviated MP. You don't really need to know the modus ponens part, but you do need to be able to interpret this table, this truth table, and be able to go row by row looking for any row that has all true premises and a false conclusion. If you find that, even just one row, the argument is invalid. And since you don't find that, the argument is therefore valid. That's how you interpret the truth table to determine whether an argument is valid or not.